Hello guys, am I audible? Okay, fine. So yeah, as I was saying, we were looking into mass transfer and some of the concepts related to mass transfer, like let's say distillation. We looked into drying and adsorption and so on, and even the general Fick's law of mass transfer. So let's take a break from mass transfer, and for the next few weeks, we'll be looking into chemical reaction engineering or CRE. So we'll start with the CRE1. So just a second. Let's set the okay. So CRE1, the major topics are it starts with rate of a reaction, and like we'll look into how we can find the rate of reactions of different orders and different kinds of reactions, series, parallel, single reaction and multiple reactions and so on. And then we'll go into ideal reactors. So ideal reactors, you might have heard batch, uh, mixed flow or CSTR, and then plug flow or PFR reactors. And these are like the basic topics for CRE1. And of course, you will have some other designs as well, like for example design of reactors for single and multiple reactions. Then you will come across various terms like selectivity, yield, and so on. So yeah, this is just a vague classification of some of the topics, the basic topics of CRE1. And today's session will mostly like spend time focusing on these concepts, and then if we have time we can start doing some problems. So yeah, let's see how far we can go with the concepts today, and like based on the concepts that we learned today, and we'll be trying to solve some problems today and in the coming weeks as well. Clear? So yeah, let's get into the thing. So before we like proceed further, can anyone like say what chemical reaction engineering is about? Like what are we trying to learn from chemical reaction engineering or study using chemical reaction engineering? Any guesses? Okay, so chemical reaction engineering or CRE. Okay, to design a reactor. That is a good answer. Anyone else want to like have a go? Okay. So CRE, the most basic information that we can get from CRE is information on reaction rate. So information on reaction rate or kinetics. So we want to see how a reaction proceed. We want to see how far a reaction can proceed, and we want to see the effect of operating variables. So these are like the basic information that we get through CRE, and of course, all these things will lead up to designs of reactor for given reaction or given kinetics and so on. Right. So The basic thing, so we have even like mentioned it again and again here, a reaction rate. So what is the rate of a reaction? Like in layman or like very simple terms, like can anyone say what do you mean by rate of reaction? So rate of reaction is basically just how fast a reaction can occur, like in a very very simple and vague term. How fast can a reaction occur with the given variables and operating conditions? Yeah. So this is the most basic thing in CRE, reaction rate, and we'll see how reaction rate like varies with the order and what is the order of a reaction and so on. Okay, so yeah, you might have learned this equation. Reaction rate usually is denoted by Ra, and it is basically a function of temperature and concentration. Okay, and the most basic representation of reaction rate is minus Ra is equal to K Ca raised to n, where this K is the reaction rate constant. This n is the order of reaction, and Ca is the concentration of reactant. Okay, so these three terms constitute a basic rate equation. So this rate can also be defined as follows: 1 by V into dNA by dt. So this is another basic representation of rate, and here V is the reaction or reactor volume, and dNA is the change in number of moles of reactant A, and dt is the time or change in time. Okay, so this reaction rate, the unit, is usually represented as mole per meter cube second. Okay, so this is the unit for this representation of reaction rate. And we can even go one more step. So Na, we have Na by V. So basically the number of moles of A by volume will give you concentration of A. Right, you can even check it in terms of the units. So we have mole Na. One second. Yeah. Yeah. So we have the unit of Na is mole per meter cube second, and the volume V. Oh, sorry, it's not mole per second. Right. So Na, the moles is I mean number of moles, the unit is mole, by V will be meter cube, and this is nothing but the unit of concentration of a substance. So we can rewrite this rate equation minus Ra is equal to dNA by V for a constant volume. So I'll write this in this page. So yeah, minus Ra is equal to 1 by V dNA by dt, which can be written as dNA by V by dt. And we just saw Na by V is Ca. So this will be dCa by dt. Now, this is applicable only when V or the volume is constant. or such systems are called constant volume systems. So that means this volume does not vary with time or temperature. So here we only look at the variation with time because the denominator is dt. So the volume does not vary with time. So some examples for constant volume systems you can take liquid reactions, liquid phase reactions. Generally, liquid phase reactions are considered constant volume systems. Whereas when you go to something like a gas phase, the volume constantly changes with time, and the volume changes as the reaction proceeds. That means the volume changes as the time or the reaction proceeds. Okay, so this dca by dt is the reaction rate, and the other representation for reaction rate is kca raised to n. Okay, so we'll be using this a lot to find the rate of reactions for different order reactions. Now, when we talk about order, so can anyone say what is the order of a reaction? Like in very simple terms, this order of a reaction is nothing but an experimental quantity. So this is basically the sum of exponents of the concentration term. Okay, like this is the very simple explanation for order of a reaction. And K, as I said, is nothing but the rate constant. Okay, so let's say we have a reaction where A is equal to B, and the reaction rate is given as Ra is equal to K into Ca. That means the order here is 1 because this is just Kca, so it is Kca raised to 1 and the order is 1. Now, instead of Kca, if the reaction rate is defined as Kca square, then the order will be 2. Or if this is Kca raised to 3, then the order will be 3. Now, another case, a simple reaction A plus B gives C. And if the rate of the reaction is defined as Ra is equal to K CaCb, here the order will be 2 because Kca raised to 1 and Kcb raised to 1, and we just saw this order is nothing but the sum of the exponents of the concentration terms. So that is 1 plus 1, and that will give you 2. And similarly, if the order is defined as R is equal to K Ca raised to 3 and Cb raised to 5 or whatever, then the order will be 8. Now, usually this doesn't happen in generally. The maximum order like we'll usually encounter in general cases will be 3. Okay. Yeah. So, yeah, this is how we represent a rate equation. Now, so we learned the rate equation and we saw there is a constant or rate constant associated with it. Okay. So this rate constant, now we earlier we just said that rate depends on is a function of temperature and concentration, right? So when we write Ra is equal to Kca raised to n, this is the concentration dependent term. This rate constant is the temperature dependent term. Okay. So rate constant is constant for a reaction at a given temperature, but then the rate constant varies with temperature. So rate constant is dependent only on temperature mainly. Okay. So the temperature dependency of reaction rate or the rate constant K, we can write it as K is equal to K0 T raised to M E raised to minus E by RT. So K the is the we know the it is the rate constant, and K0 is known as the frequency factor, which is also constant. Frequency factor. T is the temperature with M as its exponential, and E is the activation energy, and R is the universal gas constant. Okay, so this is the temperature dependency of rate equation or the rate constant. Now, generally there are three theories which explains this temperature dependency of the rate constant. So, the first and the most used constant is the Arrhenius relation, or Arrhenius theory. You can write it like this. So here, what Arrhenius says is this M is zero. Okay. So the temperature, the rate constant, we can write it as K is equal to K0 T raised to 0. So that will be 1. So we don't need to write it here. So K is equal to K0 E raised to minus E by RT. Okay. This is one of the most used terms for temperature dependency of rate constant. Okay. Now we can even take a case like this. So we have a rate constant K1 is equal to K0 e raised to minus E1 by RT1, and K2 is equal to K0 e raised to minus E2 by RT2. Okay, so let's say K1 and K2 are reaction rate constants of two different reactions. So if we divide these two, K1 by K2 will be equal to K0 will get cancelled, e raised to minus E1 by RT1 minus of minus E2 by RT2. Okay, we can take log of this, and if we take the logarithm of this, we'll get, so we'll take ln K1 by K2 will be ln of these two terms, that we can write it as, so ln of exponential, you can cancel out the e term and the ln term, because ln of exponential gets cancelled. So what we'll get on the right hand side is, okay, uh, yeah, so there is one more thing we need to notice here. So I said K1 and K2 are for two reaction rate. No, it's actually K1 and K2 e raised to minus E and minus E. Yeah. So K1 and K2 are the rate constants for the same reaction, let's say A to B, happening at two different temperatures, T1 and T2. Okay. So that was a mistake from my part. So K1 and K2 are the reaction rate constants for the same reaction and let's say it's A to B, but happening at two different temperatures, T1 and T2. The activation energy for a reaction is always constant. Okay, so there's no E1 and E2 here, it's just E. So we can just take this minus E by R, which is constant outside, and we can just write it as 1 by T2 minus 1 by T1. Okay, this is K1 by K2, right? So if you take minus E by R, 1 by, sorry, just some mathematical errors. So this is just 1 by T1 minus 1 by T2. Okay, so this is the logarithmic form of Arrhenius equation for rate constant. Okay, so I'll just repeat it again. We are just taking two rate constants of the same reaction, but the reaction happening at different temperatures, let's say T1 and T2. So we will have K1 is equal to K0 e raised to minus E by R T1, and K2 is equal to K0 e raised to minus E by R T2. And we can divide these two equations, and we can take the logarithm of these two equations, and we'll get the final expression as ln k1 by k2 is equal to minus e by r the whole into 1 by t1 minus 1 by t2. So this equation you will have to use it. There are a lot of questions from GATE where you just have to apply this equation directly, and sometimes they would have asked you to find the activation energy for a given reaction, or sometimes they would ask you to find one of the rate constants or one of the temperatures. So it is better to like note this equation. So it is there are a lot of questions where you can find the answer straightforwardly by just using this equation. Okay, so that is for Arrhenius temperature dependency. Now the other two theories. So one is called collision state theory or collision theory, and the other is transition state theory. For these things, for collision rate, the theory says that m is equal to 1 by 2. And for transition state theory, it says that m is equal to 1. Okay, so that means if you write rate constant in terms of collision theory, it will be k is equal to k0 t raised to m, which is 1 by 2, then e raised to minus e by rt. And transition theory, according to transition state theory, k will be equal to k0 t raised to 1 because m is 1, e raised to minus e by rt. Okay, yeah. So these are the three theories which tells us how the reaction rate constant is dependent on temperature. The most widely used one is Arrhenius equation, but then these collision state theories and transition state theories are also used in some cases. Okay, fine. So yeah, these are some of the basics for our basic rate equation. Now let us see how we can derive rate equations for different orders of reaction. Okay, so the first case is zero order reaction. So that means n is equal to 0, right? So rate of reaction minus Ra is equal to dCA by dt, and this will be K Ca raised to 0, or this is just K. Okay, so how do you find the rate equation for this? It's pretty straightforward. Just have to integrate this dCA by dt term. Okay, so we know that minus dCA by dt is equal to K. So CA will be what? Integral of K dt. Oh, sorry. Integral of dCA will be integral of K dt. Now this CA will vary from CA0, which is the initial concentration, and CA, which is the final concentration. And dt will vary from 0 when time t is equal to 0 to time t. So just integrate this. We'll get the final answer as CA0 minus CA is equal to KT. So this is the general equation for zero order reaction. Okay. So some of the examples of zero order reaction can be, let's say photosynthesis. Photosynthesis, is the process by which plants take up oxygen and produce chlorophyll, right? So photosynthesis is a very good example for zero order reactions, right? So if you want to plot this equation, we can even plot this equation like this. Let's say this, we'll take CA in the y-axis and time t in the x-axis. The plot will come something like this, where you know the slope is k, because this is pretty much an equation which represents y equal to mx plus c, right? So at time t equal to 0, CA will be CA0. Okay, fine. Okay, what else can we do with this? Right. So, one more thing we need to note. So, we said that Ca is the final concentration and Ca0 is the initial concentration, right? There is one more term here, Xa, which we can term it as conversion. So XA or conversion means how much of your initial reactant is being converted to the final, product. So what we can do is we can actually correlate Ca0 and Ca using this conversion. Okay. So Ca, Ca is equal to Ca0 into 1 minus Xa. Okay. So this equation here, Ca is the final concentration, Ca0 is the initial concentration, and Xa is whatever the fraction of A that got converted, right? So what will 1 minus A be? 1 minus A will be the fraction of A that still remains in the reactor. So Ca will be Ca0 into the fraction of A that remains in the reactor. So this is like a general correlation between the final and initial concentration with respect to the conversion. So now we can apply this Ca is equal to Ca0 into 1 minus Xa here in this equation. So it will become Ca0 minus Ca, which will be Ca0 into 1 minus Xa is equal to Kt. Okay. We can solve for this equation, and you will get Ca0 into Xa is equal to Kt. So this is also another form of our zero order reaction rate equation. So this equation is is pretty important. Like it's better you remember this correlation, the final concentration with respect to the initial concentration. Right. Let's move on. So far, is it clear to anyone? Like, do you want me to repeat any of these integrations? I'm just zooming through this because these are just some of the basics you might have learned in your class. Shall we move on? Okay, fine. So we saw the rate equation for zero order. Now let's move on to first order. So here n will be 1. So how can we proceed with this? The rate will be minus dCA by dt. This will be k Ca raised to 1. Okay. So same like what we did in the zero order case, we just have to integrate this whole equation. This is a simple step integration. So minus dCA by Ca is equal to k dt, and we just have to integrate it from Ca0 to Ca, and time t is equal to 0 to time t. We'll get minus ln Ca0, sorry, Ca by Ca0 is equal to kt. Okay. Or if we take this minus term inside, we can write it as ln Ca0 by Ca is equal to kt. Right. If we want to take the exponential of this to eliminate the logarithm or ln term, we can take the exponential of this and we'll get the final equation. From this equation, we can get Ca is equal to Ca0 e raised to minus kt. Okay. Now, if you want this, first order equation in terms of constant, the conversion, we can also do that because we learned that, Ca is equal to Ca0 into 1 minus Xa. So, Ca by Ca0 will be just 1 minus Xa. So, just have to substitute this equation here. So, it will be ln minus ln 1 minus Xa is equal to kt. So, this is another form of the first order equation. Okay. So yeah, and we can even apply this here in this equation as well. So Ca by Ca0 will be e raised to minus kt, and that will be 1 minus Xa is equal to e raised to minus kt, or Xa is equal to 1 minus e raised to minus kt. So you can do a lot of these mathematical manipulations to get various different forms of this first order equation. But the most generally used form is this in terms of concentration, and this in terms of the uh, you know conversion. Okay. Okay. So yeah, this is for the first order. And if you want to go into multiple orders, or like let's say the second order. So here n is equal to 2. Same thing again, minus Ra is equal to minus dCA by dt is equal to k Ca square. So, minus dCA by dt by Ca square is equal to k dt. And if we integrate from Ca0 to Ca, and this from 0 to t, we'll get the final equation as 1 by Ca minus 1 by Ca0 is equal to kt. Okay. So this is the general equation for second order. Now we can actually use a general formula to find orders which are greater than 1. That means, order uh, from order 2 and 3, 4, 5, 6 and so on. So for order greater than 1 or n greater than 1, we have a general formula which will be n minus 1 kt is equal to 1 by Ca raised to n minus 1 minus 1 by Ca0 raised to n minus 1. Okay, so this is the general form of any rate equation with order greater than 1. Because if order is 1, this n minus 1 will become 0, and Ca raised to 0 and Ca0 raised to 0 will be 1, and the right hand side will be 1 minus 1 0, and the left hand side also n minus 1 1 minus 1 will be 0. So for any order greater than 1, we can use this general equation and we can find the corresponding rate equation of that given order. Okay, so let's say if we want to find the order or the reaction rate with order n is equal to 3, we can apply this formula here. So n minus 1, so that is 3 minus 1, 2 kt will be 1 by Ca raised to n minus 1, which will be Ca square minus 1 by Ca0 raised to n minus 1, or Ca0 raised to 2, Ca0 square. Right. So using this, you can even find higher orders like 4, 5, 6, and so on. We can just do substitute the orders n in this equation, and we can find the corresponding rate equation. Okay, fine. Now, another thing we want to learn, uh, a special case, I would say, second order reaction, A plus B gives product P, the reaction rate constant K. So the difference here is, previously the rate equation was Ra is equal to dCA by dt, which was just for a second order. We just looked it as kCa square, because we assumed a very simple reaction here, A equal to A giving B. So the rate depended only on the concentration of A, and the order was 2. So the reaction rate Ra is equal to kCa square. Here the rate equation depends on the concentration of both A as well as B. So the reaction rate will be K, Ca and Cb. What can we do here? Here also the process is pretty much the same like the older case. Just have to integrate. The only problem is there are multiple variables here. So earlier it was just Ca and T, and it was a pretty simple integration. Here we have to do some manipulations, and let's say we can find the rate equation. And this is something I would like you guys to try it out. Just try it out by yourself, and using the concepts that you learned from here, as well as you can even use a lot of other materials as well, and see if you can derive the equation for this array. So that is like a homework for you. Okay, fine. Let's skip. Let's move on pretty quickly to ideal reactors. Okay, so Yeah. Uh, Fine. So, as I said, ideal reactors, there are three types of ideal reactors: batch, CSTR, or you even term this as MFR. So, CSTR stands for continuous stirred tank reactor, and MFR stands for mixed flow reactor. Both are pretty much same, just a difference in the naming. Okay, and then PFR, which is which stands for plug flow reactor. Okay, fine. Let's start with batch reactor. So, batch reactors here. Can anyone want to say, what do you mean by batch operation or a batch processing or a batch reactor? So batch reactor means you process, um, let's say you have this much amount of react or reactant, let's say the volume V, and you put it in a batch reactor, which is also V, and we'll get the final product. So basically, you take this reactant, some amount of reactant, put it in the reactor. Let's say the operating or the reaction time is 1 hour. So you put this reactor inside the reactor for 1 hour. Just wait for it. After 1 hour, you collect the product out, and then after this reaction time, you take the next set of reactant and put it in the reactor again, and take out the product time. So basically, you are just operating it step by step, not exactly step by step, but one set of reactants at a time. This is called as a batch operation. So usually in industrial scale, batch operation is not preferred because it is less efficient, because as I said, you put some amount of reactant and you have to wait for 1 hour to process the next set of reactants, and that is not economically feasible, and the production rate will be very small. Okay. So usually batch reactors are not used in industrial scales. Some places where batch reactors are used will be pharmaceuticals. Okay. So like in pharmaceutical industries, there are cases where you use batch reactors for it. Fine. So yeah, let us uh, let us move on. So we have a batch reactor V with the volume V. Let's say Na is the number of moles fed into this system. So let me just redraw this. Okay, fine. So let's say we have a reaction A gives B, and V is the reaction volume. Let's say Na0 is the initial amount of moles of A that we are feeding into the reactor, right? So we can write a material balance for this, and Na is the number of moles of A that comes out of the reactor. Okay. So if we write a material balance for this reactor, A in minus A out is equal to A reacted plus A accumulated. Okay, fine. To avoid confusion, I'll say something. Okay, fine. So the concept with batch reactor is when the reaction happens, there is no A that is coming inside this system, and there is no A that is going out of this system. Okay, because it is a batch reaction. So once you start the reaction, there is no more feed that is going inside the reactor, and there is no more product that is coming out of the reactor. So that means A in will be 0 and A out will also be 0. Okay. Now, A reacted, you can get this term by using the reaction rate minus RA into V, right? And A accumulated is nothing but rate of change of moles of A with respect to time. Okay. So this will be 0 here because A in and A out are 0. There is no A going inside the reactor, and there is no A that is coming out of the reactor in a batch operation. So if we rewrite this, yeah. So if we rewrite this, 0 is equal to minus RA, which is the reaction rate, into V plus dNA by dt, or dNA by dt is equal to minus RA into V. Now we uh, previously said that Ca is equal to Ca0 into 1 minus Xa, right? We can write an equation for Na as well, because Na is equal to Na0 into 1 minus Xa, and for constant volume cases, if we divide this equation by V, we'll get Na by V is equal to Na0 by V into 1 minus Xa, and that is nothing but Ca is equal to Ca0 into 1 minus Xa, right? So for constant systems, Na is equal to Na0 into 1 minus Xa. Just put this Na is equal to Na0 into 1 minus Xa in this DNA term. So if we Na0 is constant, so minus Na0 d d of 1 minus Xa by dt is equal to minus Ra into V. Okay. So just do the integration here, like not integration, the differentiation. So it will be Na0 into dxa by dt is equal to minus Ra into V. Okay. So this is similar to that term where for rate equation we wrote dca by dt is equal to minus Ra, right? So this is pretty similar to that term. So now all we have to do is just integrate this. So let's say we'll take Na0 into dxa by minus Ra into V is equal to dt. Okay. So just in now you see here we have Na0 divided by V. So that will give you Na0 by V dxa by minus Ra is equal to dt. or Na0 by V is Ca0. Ca0 into dxa by minus Ra is equal to dt. Now we just have to integrate this. So this will be integral 0 to xa, and this will be 0 to time t. So this right hand side 0 to t dt is t, or we can write it as t batch is equal to Ca0 into integral of 0 to xa dxa by minus Ra. Okay. So this is the general design equation for a batch reactor. Let us write this again. For batch reactor, T batch is equal to Ca0 into integral of 0 to xa dxa by minus Ra. Okay. Now we can write this in a different form as well. So we have Ca, right? Ca is equal to Ca0 into 1 minus xa, right? If we differentiate this in terms of time, or just take the differential of this, so dCa will be d of Ca0 into 1 minus xa. Now Ca0 is constant, so we can take this out. So Ca0 into d of 1 minus xa, and d of a constant or d of 1 is nothing but 0. So just write it as Ca0 into minus dxa, right? So dCa is equal to minus Ca0 into dxa, or Ca0 dxa is equal to minus dCa. Just substitute this equation here, because we have Ca0 and dxa. So we can rewrite this equation as integral of Ca0 to Ca minus dCa by minus Ra. So this is the general equation for design of a batch reactor. Yeah. So we can even plot this. So if we take uh, 1 by rate and conversion here, this plot is with respect to the first reaction. So if we take this, we'll get a plot like this. And the area under this curve will be T by Ca0. And if we take the plot with respect to the second equation, we take 1 by minus Ra and Ca. So the plot will be like this, where this will be Ca0 and this will be Ca. And the area under this curve will be T. Okay. So these are some of the things that you have to note when it comes to design of a batch reactor. Okay. So yeah, we learned quite a lot of stuff today. Any doubts so far, like in with regards to the batch reactor, or even the rate equations, how to find the rate equation for certain orders? Any doubts? You want me to repeat anything? Can I get a response? Okay. Okay, fine. let's stop here for today. So the next class we'll be learning about the design of the continuous reactors. Continuous reactors means the CSTR, the continuous stirred tank reactor, and PFR, the plug flow reactor. And from then there on, we'll see what we can learn. We can learn about variable volume reactors. We can look into multiple reaction systems, and before we proceed to more concepts, we'll try to solve some problems with the concepts that we learned today in the next class. Okay, so yeah, that's it for today. And yeah, thank you for joining. I hope this session was useful to you in some way. And I hope to see you all in the next week.